We are going to hear from Louis Ho about fuel and fueling in other galactic centers. Louis?
So I designed the title of this talk with Paul in mind. As you all know, the Galactic Center is one of Paul's favorite targets. And indeed, it was a target that drew me to astronomy 35 years ago. So I have a particular affinity for the Galactic Center. But today I'll take you outside of the Milky Way to all galactic centers in galaxies. Even for the people who study planets and star formation, of course, you must have heard that black holes are now considered to be standard equipment in galaxies because of the extremely high occupation fraction of supermassive black holes. To zeroth order, every massive galaxy has a central black hole, 10 to the 6, 10 to the 9, 10 to the 10 solar masses, and greater than 50% even of low-mass galaxies, some of you may not know this, also contain the central intermediate mass black hole below 10 to the 6 solar masses, down to 10 to the 4 at least. That's one part of the story we learned from the Hubble Space Telescope. And the other is that these black holes and their growth and the energy and momentum that they release back to the environment have potentially a profound impact on the evolution of galaxies. Some people would even say that they control many aspects of galaxy evolution. So we want to understand as much as possible about these more physical questions about the fueling, the amount of fuel available, and also the energy they release, and whether AGN feedback, as it's called, is truly as effective as the theorists would lead you to believe. To address this problem, besides knowing the mass of the black hole and their bolometric luminosity, I consider that the three most important but also challenging ingredients to measure correctly is the stellar mass of the galaxy, the star formation rate of the galaxy, and also the cold interstellar medium of the galaxy. By galaxy, I mean galaxies that have black holes, and they all have black holes. Okay? What is the challenge? The challenge is when the black hole shines, we call it AGN, it's actually very challenging to disentangle the signal of the galaxy from the bright nucleus, which can really outshine everything, especially when we call them quasars, and especially if they're at very high redshift. Now we know quasars as far back as redshift 7.6, AGNs as far back as 11 from JWST. So with those redshifts, we have very little signal noise ratio and very, very little spatial resolution. But we have to disentangle these quantities. To do so, you need a variety of tools. I can't possibly review them, but let me just say that we made tremendous progress, and basically we've solved most of these challenges. To measure the stellar mass and the stellar age of the host galaxy, first and foremost, you need to have images that are very high resolution with a stable PSF. In the past, that's HST, now it's JWST. You need to have an effective way to analyze the data with two-dimensional and indeed three-dimensional techniques. And you need to be able to fit all these data together because we want in the end not light, but we want the stellar mass. These problems have basically been resolved after many years of effort. Gas comes in many flavors, atomic, molecular, interstellar medium, dust, it's ionized and so forth. H1 is incredibly challenging because we can't really go beyond the local universe at the moment. And there are no quasars in the local universe. CO is good, but it's very expensive. But even if you could detect it, we have this so-called alpha CO factor that people have been debating for decades, seemingly to no resolution. I propose, and we've devised methods to bypass all of that by going directly to the dust. If you can have a robust measurement of the total dust mass, then via simply half a free parameter, I maintain you can obtain a very robust total interstellar medium mass. You can resort also to dust absorption. PAHs are incredibly versatile. Remember, they come from the PDR. for the dissociation region, which is closely associated with GMCs. And with the advent of JWST especially, it's extremely powerful too, because now you can do this in space and also with IFUs. Okay? Star formation rates. Contrary to popular belief, this is a really, really uncertain area. It's not enough in the case of a normal galaxy. You have many tricks you can play across the spectral energy distribution, from continuum, from emission lines, whatever. But once you turn on the accretion disk in the torus, that's what the NAOJ does, all hell breaks loose. You can assume that you know what's going on, like the far infrared coming from star formation, but ladies and gentlemen, that's a very bold assumption. I've abandoned all these assumptions, and through several PhD theses, we've invented new methods that involve optical lines, the infrared lines, and neon, pH lines, recalibrated traditional methods, and invented new ones. And let's just say that I'm comfortable enough to start to use them for science. Okay, so this is essentially, we're in a better situation than we were, say, 10 years ago. Okay, so those are the tools. For the rest of the talk, I'll just tell you we have them. Now I'm going to summarize some results, starting with some old stuff from Arecibo. The bottom line is if you examine in detail the H1 content of nearby AGNs, they look the same as in normal galaxies. That is, the specific H1 mass is no different than star-forming galaxies of similar mass and probability. Not only the amount, the kinematics are also incredibly regular. For example, the line widths obey the Tully-Fisher relation. So even though I have no spatial resolution with these single-dish spectra, I can infer that the spatial distribution can't be too wacky. Okay? So these AGNs, they're not experiencing blowout. No way. Otherwise, why is the gas there and why is it rotating, the way it should? That's H1. Now let's go to the total cold gas, as I said, from dust emission, which very quickly summarized. For a large sample of the brightest local quasars, 87 PG quasars, less than 5, they have an absolutely normal cold gas content. The gray points are the control sample of star-forming galaxies, the blue points are the quasars. You can see they distributed the same. Type 2 quasars, those that are obscured and presumably the progenitors of type 1 quasars, behave in the same way. These are the red points, the type 1 quasars, the blue points, and the control of the gray. Highly obscured systems, people call them Lurgs and Eulers. They're all massive galaxies, they all have black holes, they're all accreting. Many of them have AGNs, have X-rays, etc. They're basically the same as well. So no matter what you're looking at in these different scenarios, evolutionary phases, the co-ISM simply is not exception. This poses a severe challenge to most of the theories that you've heard and most of the movies you've seen that advertises spectacular blowouts and quenching and all of that stuff. Okay? Okay. Are you sure we have reliable gas masses in the dust? For a significant fraction of the objects we've gone after with ALMA, ASIAA, clearly, easily detected, CO. It's abundant. And so that confirms the gas masses are robust. They have normal line widths. They obey what I call CO-Tully-Fisher relation. And the profiles are just as you expect for a rotating disk. Okay, so there's no evidence for high velocity wings, strong outflows, strong constraints on basically we don't see evidence for outflows. For a subset, we've gone with higher resolutions with ALMA, and again they are regularly rotating, normally distributed. The one thing that's very interesting is that the gas is quite compact. So unlike star-forming galaxies, which have half-mass radii of a few kiloparsecs, all these quasars have half-mass radii in CO about 1 kiloparsec. So they tend to be concentrated towards the center. We can do the same thing at similar resolution with MUSE, okay, now tracking the ionized gas. We do see evidence of ionization cones and various perturbations and all of that, okay? But this doesn't carry much mass or momentum. At the end of the day, we do see ionized outflows, but they're very, very poorly coupled with the bulk of the interstellar medium. And they don't contribute much to feedback in these galaxies, in these AGNs. Now we can do this with JWST. This is just the first example. Nearby AGN in Euler, okay, with new mid-infrared diagnostics, which is just beautiful. You can access not just star formation rate, shocks, ionization parameters, temperature from all the molecular hydrogen lines, pHs, velocities, and so on and so forth. We see, again, mild evidence for non-virial motions, but they actually have a minimal effect on the star formation rate or star formation efficiency of this system. It is not doing much in terms of affecting the evolution of these systems. So, they're forming stars, I told you, but let me just show you the evidence, okay? So now we have very robust star formation rates in gas masses. This is the famous main sequence diagram, and these quasars, a significant fraction of them, they all basically sit on the main sequence or above the main sequence, okay? They have high specific star formation rates. More importantly, they have very low gas depletion timescales or high star formation efficiencies. This is the physical definition of starburst. So not only are they forming stars, they're forming in a starburst mode. Just like the aficionados, most are not mergers. Trying to wrap your head around that. If you want the starburst need to be triggered by major mergers. So as I said, now we have larger samples from the techniques I just told you earlier. Most of them lie on or above the main sequence. Their specific star formation rates are high. Interestingly, it increases with black hole accretion rate. The more luminous the AGN, the higher the deviation. Okay? Okay? Star formation rate is correlated with black hole accretion rate, and the star formation efficiency is correlated with black hole accretion rate. The degree to which their starburst correlates with the strength of the AGN. This is actually precisely the opposite of what has been purported for AGN feedback. Okay? But where is a starburst occurring? So for the minority objects, we have good IFU and ALMA observations. We can say confidently it's occurring in the central regions of the galaxies, within 1 kiloparsec. So these are not only starbursts, they're central starbursts. Centrally peaked starbursts. Let me summarize. This is the last slide. The gas properties have taught us a lot. Okay? Contrary to popular expectation, they're not lacking in cold gas. The kinematics of that gas is normal. Outflows are rare. However, the gas does appear to be more centrally concentrated than typical. All of these facts challenge strongly popular models of AGN feedback. In terms of star formation, again, they're not quenched. Far from it. They have normal or enhanced star formation rates. In fact, they're sufficiently high in efficiency, they qualify as starbursts. They're centrally concentrated starbursts. Okay. So they are circumnuclear or nuclear starbursts. So if you want to remember anything from this talk, every quasar is a nuclear starburst. Okay? That has powerful implications for feedback. If you thought and you've been taught that it's due to the AGN, they've neglected this blatant fact, which is completely unimplemented and even unknown to the people who write these theoretical pictures. Interestingly, the star formation rates, and the star formation efficiencies actually increase with black hole accretion rate. Okay, let me end just with a tribute once again to Paul. This was the first paper I wrote as an undergraduate, submitted when I was an undergraduate on the Galactic Center, the Sagittarius A West region, mapping the molecular clouds. We were both much younger back then. I showed this at the resort, but some of you were not there. Paul and I we occasionally observed together. This was at the 12 NRAO 12 meter at Cape Peak. I have many fond memories of this. This was just a few days ago. So I just wanted to say from one hole to another, thank you very much, Paul. This has been a wonderful journey. You gave me the beginning, and I've taken it and run with it. Okay. Thank you.
Questions? Yes.
Hi. Actually, I'm not doing AGN, so I know very little about it. In my memory, the rotation axis of torus around AGN is not aligned with the gas, the large-scale gas around AGN. Correct me if I'm outdated. But if it's not aligned, what we can tell from the correlation between the star formation and the AGN.
You're partly correct. To be more exact, the accretion disk is misaligned with the large-scale angular momentum vector of the host galaxy. We don't actually know much about the torus because that's a theoretical construct, okay? Except for the galactic center and intensity, we can't see it. But we know that the accretion disk is basically random because you can see the radial jets. Okay? Assuming that the radial jets are normal to the accretion disk. That strongly suggests that the gas falling into the center does so through, I like to think of it as clump collisions, sometimes called chaotic accretion. So by the time it gets to the very center, it's lost a memory of where it came from. In fact, we see in the galactic center fall. Okay? So you look at the circumnuclear disk, okay, it's not really aligned with the CMZ. And then within the circumnuclear disk, which is 1 parsec, there are 3 streamers. Right? They go like this, like this, like this. Okay? That's because every stage, from 300 parsecs to 10 parsecs to 1 parsec, and then below, the clumps which we see, gas is very turbulent. They collide and they lose most, but not all of the angular momentum. And then they, but every time it does that, it basically forgot about its original work.
Right, and for the case you mentioned about the Galactic Center, I believe Pei-Ying Hsieh's work both magnetic field play an important role, and also recent SOFIA polarization result also suggests the same scenario. So do you think
Important role for what?
for the regulation of angular momentum, the stream flow from the outside to inside? So do you think is that common for other regions?
I guess I need to be convinced of that argument first. When I worked with Willy Benz, I thought so too. If you look at the really mini spiral and Hildebrand's polarization vectors, they do seem to be aligned with the mini spiral. Whether it's dynamically relevant. Remember, those streamers actually have fairly Keplerian velocity. So apparently gravity dominates, not when they pressure.
Thank you very much.
Okay, thank you. Paul.
So my concern is always about time scale, right? All of these phenomena are on very different time scale, right? The black hole formation and even the activity is on very different time scale than the star formation, then the gas flow, right? So we're seeing a snapshot of various phenomena that is on its own time scale. And how to connect them all together always was a problem for me. What do you think of that?
That's an excellent question. So you're absolutely right. Okay, the star formation and the accretion, instantaneous accretion rate, and the instantaneous star formation rate is misleading. Star formation happens on a dynamical timescale of the galaxy. In this case, the dynamical timescale of the circumnuclear region, which is about, say, 10 to 8 years, a few times simply 7 years. that's also close to the gas depletion timescale, right? So that is the natural timescale of these regions. Accretion is about 2 orders of magnitude shorter, more like 10 to the 6. Okay, so there could be many bursts and many cycles for given a star formation timescale. It is precisely because of this region, and because the circumnuclear region contains 1,000 times the mass, 100 times the timescale, that I think that their energy output must be really important for feedback from galaxies. And theorists have gone crazy, because they just, enchanted by agent feedback. They insist that it's only that. Okay, I think exactly for that reason. So it's not surprising they are correlated on relatively long timescales. After all, both processes require the field. The field is cold, dense gas. So that's the main reason that they're correlated. It's not that they're causally related. Okay. Some people jump to that conclusion. I think that's it's possible, but maybe not really necessary.
It's like that correlation, star formation rate to the NAOJ rate.
Mm-hmm.
That could be just more of bigger things are more of everything.
Maybe. Okay, so some people think that this is actually evidence for AGN triggering star formation, so-called positive AGN feedback. Okay, in the same way that say supernova can trigger the molecular cloud too. That's not totally crazy, but it's still very circumstantial. I just showed you the data. You can interpret it, in different ways.
Thank you, Louis. So that will lead us into the next talk, the circumnuclear disk revealed by ALMA, environments of star formation in the inner 10 parsecs of the galaxy. And this is Pei-Ying Hsieh.
Hello everybody, very happy to see both old friends, old students and both up here. Very nice to meet you. My name is Pei-Ying, and I was post PhD student, so I did my postdoc here in G for several years, and now I am a faculty, I got a faculty position in NAOJ. So here I would like to tell you something about the Kavli Center I've been working on in the recent years. And the center I'm talking about this real center is a central 10 parsec within the center of the Milky Way galaxy with a size of 268,000 parsec size. So in this image, what we see here, the blue color is the molecular gas, the neutral gas, raised by the ALMA's 76 line. And ASIAA star is labeled with this cross, so within which the ionized gas colored in red, spilling the central cavity of this ring. So here you see this tilted, this is a highly tilted ring-like structure we call circumnuclear disk. It's a disk with size about a few parsec rotating with ASIAA star. With respect to ASIAA star, together with this ionized figures. Okay, so here I would like to just to show you the previous interferometry maps of the CMD, the circumnuclear disk, from 10 arcsecond resolution to a few arcsecond resolution. And here is the evolution of the mapping. We can see based on the improvement of technology over the past 3 decades. So here, this is the 3 elements interferometry map of this HCN10 line. And the contour is the VLBI ammonia 66 emission overlay with the HCN10 line. And in the bottom, these are HCN10 S10 line made by overall. And first, HCM43 image of the CND image by SMA and by single resolution. So here we can see the pointing what was improved from 2 pointing, 10 pointing, 25 pointing, and in the later experiment we use SMA to do the 150 pointing to try to image this filaments surrounding the CND to see what's the connection and if those filaments are real. So they were detected as those protrusions surrounding the CND. And this is the same area, the image with ALMA with the 1.3 optical resolution and 600 pointing, and 7. So thanks to the improvement of the astronomical observation facilities, so I have studied several questions, several important problems in the Alexander. They are listed here from the entire central market zone made with the Nobayama 45 years ago, and I've done the nuclear auto and bubble study using the Nobayama 45 years data, and using also made the analysis of the ALMA map, and together with the previous JCMT polarization data to study the dynamical equivalence of magnetic field in this region, and to see whether the big field is able to guide gas ionized particles from neutral gas, from neutral ring, partially ionized particle from neutral ring to the central part of the CNC. But today I'd like to just focus on the gravitational stability of the molecular counts in the CND in this region. So this is the ALMA experiment we have made a few years ago. We did the no-demand observation from band 3 to band 7. So we did a mosaic to image the CND together with the filaments. So we compare our image, the 1.3 optical resolution image, to the SMA map by Mark-second resolution map. So we can see that higher spatial resolution, those clump-like structures will result into elementary-like structures, and within which there are compact clouds or these fiber-like structures of fiber is moving around in this region. So by comparing the different excitation image, you can see in the CND, the Kavli center, the excitation is certainly higher than the disk gas because the structure of the CND and its strippers are much more clearly seen toward high frequency. And so in total to make five maps. So it took 88 hours to conduct those maps. And so now the questions that we would like to ask is, there are so many compact and dense clumps detected in this region. So these pink circles, ellipticals, are the identified compact structures in this region. So there are so many compact structures detected in CS line. But why there's no clear subformation detected in this region? So there were actually the detection of the maximum masses detected overlap with those symbols in this region. CND is here, and here are actually the two regions, so there are subformation here, but here is the part of CND. But in the later high resolution, dust continuum, the high resolution map of the dust continuum there are no detection of the corresponding compact sources corresponding to these masers. So these masers are likely just produced by the top of the direction in this region because the clouds are moving so quickly here. So at this moment, so far, we don't have a clear evidence of star formation. It's ongoing in the central parsec of the big center. So we would like to know why is that, we want to know the physical properties of those clouds that we detected. And so besides the possibility of star formation on this region, another important question we want to ask is whether the gas in this region is low-life. Because we know the structure is pretty close to such a star, so the tidal force is pretty strong. So if the gas density is lower than Ocean at parsec, it is 10 to 7 cubic centimeter, then the gas will be dispersed by tidal force, and it cannot be low-life. So we want to know whether those gas they can be low-life or they have a possibility for star. So here is the stability equation we calculated to compare with the data. So we consider turbulence as the major input of internal energy, self-gravity, and external pressure. We didn't consider external pressure in this case because it's complicated here. So we omit external pressure for the time being. And we also consider the external force, the contributions from the tidal force. So here there are three cases. The first case is no tidal force, no external pressure. So this equation just goes into a typical Wheeler equation. And the second case is no turbulence and no external pressure. So this equation goes into the typical critical density term of the tidal stability. And if we consider turbulence and also the tidal force, then we will have a relation of we can calculate the critical density at specific line width, which is turbulence, and also consider the effect of a tidal force here. So these two lines basically define three regions. The first one, blue curve, is a pure tidal force. So if the gas density is lower than if the gas density as a function of such a star is lower than the tidal critical density, the gas clouds will be dispersed by tidal force. So it's like pasta. So just like spaghetti lines. So they are going to be stretched as long filaments. And between these two curves, the clouds, they are tidally stable. They will not be dispersed by tidal force, but they also cannot collapse to form a star because the turbulence is too high. Because we can see the orange curve here, this actually sets up a higher critical density to the clouds. So with the velocity dispersion of 7 kilometers per second, so only the cloud densities higher than this green orange curve, we will get a shadow cloud, we will get stars formed here, and within which are just dawn. They are very stable, they don't expand, they don't collapse. So we are going to measure densities of the gas and put those densities on this paper to see the condition in the green center. Okay, so here this is the projected distribution of individual clouds identified in the dendrogram, and the color is the log density. Because we have 5 CS transition lines, so we can use the statistical calculator to calculate the gas densities. So you can see the gas density ranges from 10 to 3 to 10 to 8. But just I want to just let you know that this 10 to 8 is a maximum. It's upper limit in our model. Okay? So it could be higher, it could be lower. 10 to 3 also it's also a parameters of the model range. So here, this is the central part, the central region of this projected 2D distribution of density profile, and this is the distance from such a star as a function of density. So now we have two curves. So we can see 94% of the clouds they are low densities. So 94% of the clouds they are they cannot withstand tidal force. They will be dispersed by tidal force in this region. But the good news is we have external force. So the external pressure, not external force, sorry, external pressure from X-ray halo. So I think about 50% of the clumps, they can be stabilized by the external pressure. So here the clumps in between these two curves are gravitational stable. But if the turbulence grows in the future, so these clumps will be unstable in the future to be dispersed by turbulence. So here we have 16 clumps detected. The density is higher enough to overcome the gravity, and they are able to collapse to most star. So this is our result. So here, the most important thing I would like to draw your attention is we can see turbulence actually sets up a higher probability of the star formation. Tidal force is important, but it is actually less important than we mentioned before. So this is a three-dimensional distribution of position and velocity of individual clumps, and the size of the clumps is proportional to line weights. So here we see these gravitational stable clumps, the green colors of clumps. They are not going to be dispersed by tidal force, but they are not going to collapse to small stars that are located in the southern part of the CND. It's interesting here. It's probably that the incoming streamers push the incoming streamers glide the southern part of the CND, and the density gets higher in this region. But in the meantime, the turbulence also get a portion of the kinetic energy from turbulence to the clouds. From kinetic energy of the temperature to the clouds, so the line width also grows. So it's kind of a competition between turbulence and compression. It's really unclear in this region what is the effect of these clumps. So here, the summary is for the 4 million solar mass, so supermassive black hole, tidal force is important. Maybe less important than we think. At least it's longer further than 1 parsec. Turbulence is much more important on the domination of the star formation. So making pasta is easier than show up. Okay. So this is my talk. Thank you very much.
So what is the driving source of turbulence?
What is the driving source for turbulence here? I think there are several functions that can cause turbulence, motion here. And one possibility is cloud collision in this region. Those incoming streamers that just go in, impact upon the CFD.
I have a friend who loves Fermi bubble. So Fermi bubble.
Yes.
What role does Fermi bubble play in this stability calculation you do? How important do you think that is?
Yeah, it's yeah. So J starts here, and this is the bipolar radial halo. So south to the J star is a expanding bubble in this area, and those J stars they are accelerating outflow. So those those outflow systems are certainly much younger than the Fermi bubble. But what we see here is the inflow structure was really destroyed the inflow feature in this region. But maybe just after some time, those gas they fall back, and the inflow structure will be reconstructed again. So this is kind of a life cycle of inflow outflow.
Now we're going to hear about future science from the Event Horizon Telescope from Jeff Bauer.
Okay. Okay, good. It's great to be here. Thanks to everyone for holding on to the end of 5 days of meetings here. It's been really stimulating, and it's been great seeing so many friends and colleagues and acolytes of Paul. These are, of course, very familiar images to everyone at this point. M87 and Sagittarius Star, two beautiful rings. And one of the things I've been musing on all week in the context of the last talk and the circumnuclear disk is that all of this represents something like Paul's three-ring circuits. We have the circumnuclear disk, and we have these two beautiful rings, black holes. So I believe that Paul's first paper on VLBI observations of either Sagittarius Star or M87 is this paper from 1998, working with Fred Lowe and Eric Chen, and one of the first papers to resolve Sagittarius Star beyond the scattering regime. And then this paper, just a few years later in 2001, is the first time that Paul and I collaborated on a paper, which was another VLBI paper. You can see many of the people who have been very influential in Galactic Center and VLBI science as a part of that, and of course Jim Moran and Fred Lowe, very active and important participants in all of this. I have to say also, with all the talk about Godfathers and Mafia over the last week, I looked at this photo and I thought, well, maybe this is the last thing that you see before you get whacked. Okay, these images, I think they've had such a broad impact and really have reached the farthest corners of our global culture, and this is only a short sampling of all the means. For me, the XKCD cartoon is the highlight, just because it includes both the science and a bit of a whimsical characterization of it, and really, quite strikingly that this M87 image has a diameter of essentially the outer solar system. The Sagittarius Star image, where the black hole is 1,000 times less massive, has a diameter about the orbit of Mercury. Okay, so all of this is work that's been done by hundreds of people. This is the photo from our collaboration meeting in Taichung over the summer. There were about 100 or 120 of us present for this meeting. The EHT, which Paul has been was very influential in founding and has been very influential in guiding since its founding, has members in more than 24 countries and regions around the world. There are over 350 members at this point in dozens of institutions, and really representing the entire ladder or range of different activities within our profession, all the way from technicians, engineers, telescope operators, to theorists and and observers and algorithm experts. And so that's a really great part of the strength of this collaboration is the breadth of people, and of course all the young people who bring so much energy and enthusiasm to this work and do a lot of the really hard work of producing these results. So what I want to do today is just very briefly go through kind of the highlights of what we've achieved, and then talk about where we're going, because really this is just the beginning of the road. It's not the end of the road. So first, primary EHT results: black holes power active galactic nuclei. You know, when Lewis tells you there's an AGN and there's a black hole at the and in that AGN, well, that's a 60-year-old question of what powers the AGN. And now, when we go from these large-scale jets that you can see in this beautiful multi-wavelength portrait BAM87, and as you go all the way down in spatial resolution, right, there's this beautiful ring, and interior to that ring is the black hole itself that is powering all of this emission and driving large-scale features that are beyond galactic scale, right? They are cluster-scale features in these systems. The second area where EHT has had an impact is that there we go. Our measurements test general relativity over 3 orders of magnitude in black hole mass. Right? That ring has a diameter that is exactly predicted by general relativity, and to the precision with which we can measure it, and we agree exactly with the prediction of what general relativity gives us, and that's quite powerful. It occupies a part of the phase space of tests of general relativity and theories of black holes that is not tested by any other mechanism. It's not tested by pulsars. It's not tested by solar system tests or cosmology or LIGO measurements. And so that really gives us a unique window and leverage on what's happening in the field of gravity. The third point is that we are making some of the most precise measurements of accretion and jet physics. The way you're seeing here are models, GRMHD models that are produced by members of our team, and each one of these models represents a different parameter set: inclination angle, mass accretion rate, magnetic field strength, electron temperature distribution. I'll play this again just because it's so entertaining to watch these things spin around. So they represent the whole range of what's predicted at higher angular resolution, of course, than we can actually observe. And then these are being chipped away by all the different measurements that we make as a part of our EHT observations. And you can see that we in fact have very strong constraints on the mode of accretion and these physical parameters. And in fact, in the case of Sagittarius star, none of the models survive the tests, the observational tests, which is a really fantastic thing as an observer to be able to say. We're giving work to the theorists, right? Yeah. Okay, so what's next for the Event Horizon Telescope? We've only shown you a very little bit of the data that we have already taken. We published results from before 2017. The M87 and Sagittarius star images that you've already seen came from our 2017 campaign. We've been continuing to observe every year, except for a couple of years as a result of COVID and some technical issues. And you can see that we're growing the array over time. We're adding in new stations or enhancing their capabilities as we add them in. So the array that we're working with now is much more powerful than the array that produced that first set of data. We're increasing the bandwidth, the recording bandwidth, and we're increasing the frequency range, or the frequencies at which we observe, which is an improvement in the angular resolution by 50%. So we already have 345 gigahertz observations of Sagittae star, and in the coming year we're approved to get another round on Sagittae star, and the first 345 gigahertz observations on M87. And so that's, all of this together is really quite powerful. We're, of course, working very hard to publish all of this data, get the most exciting things out to you. Stay tuned, there's a lot to come out in the very near future. We've observed a lot of sources. We've not only observed Sagittae star and M87, we've actually observed a really wide range of sources. Some of them are kind of classic blazars, things like VLBI, but many are interesting nearby objects, and we see all kinds of interesting morphology. And in fact, we've published a number of papers on jets in some of these nearby sources, for instance, in the Centaurus A, and there are results coming on many of these. Some of these sources are near the threshold at which we might resolve angular structures in them, or circular ring structures in them. And there are a wider sample that we're going to continue to observe in the future. So in the last year, we went through an exercise within the collaboration to define our future and what we wanted to do. And we came up with 4 questions. The first one is, what is the origin of relativistic jets and supermassive black holes? This is a simulation just showing the relationship between the accretion disk and the formation of the jet. And of course, M87 has this beautiful jet, and we know it's a dynamic system. Dynamical timescale for M87 is about 100 days. And so one of our major observational goals over the next several years is to do a multi-epoch observation over about 100 days and sample a rotation period around the black hole and see the connection between the accretion flow and the disk. Sagittae star, on the other hand, evolves very rapidly. The orbital period for Sagittae star is about 30 minutes. It's also, it also has really great dynamics in terms of X-ray flares and near-infrared flares. And so connecting the variability that we see in the image domain with the variability that is observed in multi-wavelengths, a really important domain for testing the formation of shocks in these systems and the excitation of particles, and really addressing some long-term questions in that area. The third question is around, do supermassive black holes have strong magnetospheres that extract spin energy? And so this is an idea known as the Blandford-Zignayak effect, in which the energy is actually extracted out of the black hole through the process, through the magnetic field processes in the accretion flow. We've already published a polarized image of M87, and we expect to be able to push that, improve on this image and see more details. There are almost there. There are imaging signatures within the polarization features, which we believe will be quite powerful for that. And then polarization itself turns out to be a very powerful diagnostic of many of these modes of accretion. You can separate out the orientation of spin and different modes of accretion. Final question, and I think maybe this is the most important one, is how can we constrain the properties of space-time? And here I think Sagittae star is perhaps the most important of these objects, in part because from the measurements from Gensel and Des, we know the mass and the distance of Sagittae star to an accuracy of 1% or better. And that means that all the predictions for the ring diameter are known very accurately. And there are actually a whole ensemble of different kinds of measurements as we go to higher angular resolution, higher dynamic range images that allow us to measure the spin of the black hole and test alternative theories of gravity and alternative theories of compact objects in black holes. So how do we get there? There's a whole slew of technical developments that members of our team are at work on around the globe. Observing agility is one of these. It used to take a team of 5 to 10 experts to fly into each station in order to be able to carry out our observations. We can do that much faster now, and that's really important in terms of getting better weather and also in terms of being able to make movies as we want to do. Going to higher frequencies gets us the better angular resolution and a test of achromaticity, which is one of the most important predictions of general relativity. Improvements in recording, and there are a number of efforts now to increase the number of sites. As you already saw, we've been adding sites along the way. We have additional sites that will be coming online in the next year or 2 years. One in Korea, sites in Owens Valley and Haystack, and then beyond. And then in the very long term, going to space really gives us extreme angular resolution, more sources, and deeper physics. And she stood up and I'm done.
Thanks, Jeff.
And I brought the pointer.
Questions or comments?
I was just wondering, in terms of funding for those new sites and new telescopes, if you can comment on that.
Every telescope is unique, so Owens Valley is repurposing one of the Karma 10-meter antennas. And they've had NSF funding for that, and Haystack has gotten NSF funding for its upgrade. It probably needs a little bit more to finish that. In Korea, I don't actually know the ins and outs of the funding, but it's a part of the KVN system, and so it's the telescope is being built to be a part of the KVN and also will contribute to the UHD. In Europe, Heinrich has raised money for the Africa millimeter telescope, which will go into India, with various European sources. And then there are funding opportunities in the US and around the world to try to support other sites. It's not possible to cover all of that system.
I have a quick question. Sure. When is the 345 result going to come out?
You sound like a member of our board. So the unlike the JWST when the data comes down and it's a picture on your chest, we took those 345 gigahertz observations that is our last April. And we are accumulating the disks at the correlator stations right now. We have to wait for disks to get out of the South Pole, which doesn't happen until November or December. And then there's a period of a few months to do kind of basic checks to get the correlation going. And then you know, the actual correlation then takes 3 to 6 months beyond that. So it's a year away, optimistically. But it is actually, I think, a really high priority for us. Definitely one of the challenges is that we have such a high standard for the analysis that we carry out in our papers. We do multiple redundant analyses, and our results are very, very rigorous, but it also does mean that the pace of getting those results out is not as rapid as we would like. But expect some new stuff very soon.
Great. Okay, thank you.
So now we move into the final session of this conference, and that's the session for the instrumentation and future facilities. I'm going to give each speaker a 2-minute warning at 10 minutes. All right. Okay. And in the interest of time, all right. So Jessica Dempsey will give the first talk about next generation radio astronomy development.
Maybe I have to features. Yeah. Okay, that's something completely different. I want to take you up from a real bird's eye 30,000 feet just to finish this off. A fantastic week, and I'm very stimulated by this site. I'm going to take you to some long wavelengths and some full experiments. And this is really set up by some great talks, particularly Jennifer, Pei-Ying Hsieh, who started off with thinking about this. And I want to give you an example of how you might look at this wonderful color image with the low-fi layer of Sinica, the approaching radio astronomy renaissance, particularly in long frequencies. So how can you predict the future? I think what you need to do is understand the drivers that create new science discovery space. We need to find a balance between instrument push, the ever-creators that are instrumentationists, and the science pull, and that balance is a magic place. And how do you measure the true scientific value of a scientific instrument in a non-ad hoc kind of way? And you allow all of this then to inform your future science strategy. Paul inspired me, supernovae, of course, being something I come to tackle for every time. And so, as I come from an instrument background, I do think there's some very simple recipes for how do you make a discovery engine. And I think the first one is wavelength window. Anytime you can open up a new window on the universe, you're going to find new things. So this is definitely the first way you're going to put into your new engine to discover things. The second one I'm calling dimensionality. How can you add a new dimension to the instrument you're building? Is it 1 to 2D? Is it 3D? Is it spectral? Are you going to do time domain, multi-frequency, polarization? All of these things add an element of discovery. The third one is one that's looked at most importantly, and I just call it greed. More is more. How can we make it more bigger, better, faster, stronger? Resolution, sensitivity, field of view, multi-object bank. Focusing on resolution in this week. But all of these elements, when you find that magic Venn diagram and cross these over, this is when you get those incredible instruments, those amazing observatories. And I've just sort of been schooled, if you like, in the last year and a half, as I have had to move wavelengths by a significant amount to be at ASTRON. Long wavelengths for the first time in a long time. And so I'm going to give you an example here by running you through the little instrument that could, which is LOFAR, and why this is now leading me to believe that the really big next discovery space is in low frequencies. LOFAR started as an experiment. It actually started as a test to see if we could go and search for the epoch of reionization. This is, of course, that very first glow when you started to get the reionization of the universe, everything started to cool down, and that right now is squarely in the pocket of the frequency space where we would like to use LOFAR. Of course, this is an incredibly challenging result. No one has got there yet. They're continuing to beat down on the systematics of this, but this is still 15 years in. We've got multiple projects doing this, and we're still searching for the signal now, and something SKA will do. But it was also for pre-SKA, and this is a really other instrument lesson that I have learned, which is if they had thought SKA was coming only a few years after LOFAR at that point, hey, let's get in there and do a little bit of data before it comes online. And of course, it's still a precursor today, and that is to tell you never be afraid of competing against potential future projects. This is what LOFAR looks like. It's one of the most boring telescopes on the planet. Of course, it's just a bunch of sticks in a field, but they're very powerful sticks because this is a non-moving parts telescope. So you're a digital phased array, everything is moved or steered by delaying signals or forming beams, combining groups of signals. I'll show you the map in a minute. There's 38 in a type formation in the Netherlands. And then the rest of them have been over time spread 2,000 kilometers across Europe. They have high bandwidth fibers at St. Groningen, the central processing facility. We have a processing capacity of teraflops and about 2 petabytes of temporary storage. This is what the array looks like at the moment. This is actually a little bit ambitious here. We still do not yet have the Italy and Bulgaria stations, but some of these powerful lines here you see go as far as Latvia and to Ireland. Actually, what's interesting here, when we did some mapping of where the most valuable new station would be, it actually is Belgium. We actually call this the Belgian hole, which is a great name for a bar. And actually, for the phase space, we would actually do very well with a new station there. But these long baselines are really where the magic and the new, really incredible science discovery space is happening with LOFAR. So when I was doing radio astronomy as a 19-year-old out in Narrabri, Australia, I ran screaming from the field because it was just 21 centimetre hydrogen, it was all done. And it was filled with a bunch of guys in khaki shorts and knee socks with sandals. And I was like, this isn't for me. Coming back 20 years later, and I've just had to go back to school because the science, why would not work? The science space that has been filled in the meantime is just mind-blowing to me. It's not just epic of reionization, lower upper limits. The field has grown in every single direction you could possibly imagine, and this is the other sign of a discovery engine, when you have mapped out that magic space, because when suddenly people are coming to you and doing everything from galaxy clusters and gravitational event measurements, supermassive black holes, and of course you're going to expect in the radio your pulsars and your fast radio bursts, but you're also doing things like cosmic rays, space weather, and lightning studies. And this is the breadth of the science that we're now seeing out of LOFAR. I had to put this in, especially coming after Jeff's talk. LOFAR has some value in really chasing down these backgrounds and the large scales that you can see on some of the most famous measurements that we've been seeing over the last decade. But I can't really, I could spend a whole bunch of time on all this, but I do want to really highlight that there's value in LOFAR that I never believed could exist. Blobology has always been what radio science has been called, and you never would have thought that you would be doing things where these wonderful surveys are these very, very long wavelengths. Because you have these long baselines, the potential resolution on the sky is incredible. It is simply very time intensive to go from what would be when you have just the Dutch stations, so that's, the Netherlands is very small, so you only have a baseline of a few hundred kilometers. And you have the 6 arcsecond resolution that's still excellent at these frequencies. But now we're capable of going to Hubble resolution at these frequencies. And so some of this is a wonderful Leo Morabito's work just to demonstrate the difference when you use these incredible baselines across all of Europe and you start to dive deeply into these incredible clusters and these outflows. And so when we go to SKA world, they're going to have only 70 kilometers baseline. So these 2,000 to 3,000 kilometer baselines of LOFAR will still be utterly unique in their capabilities of resolution at these frequencies. The other thing, I never dreamed we'd be seeing is exoplanet work in the long wavelength radio frequencies. And they have now successfully detected aurora on brown dwarfs of similar size, and we do believe with the upgrade in LOFAR 2, we will be able to look at Earth-like planets and potentially detect magnetic fields which are being set off by aurora in their atmospheres, and certainly Jupiter-like planets within the next several years. The final one, just because it's incredible that you can do this, you can actually real-time map through the atmosphere lightning strikes above the LOFAR arrays, and now we're actually using this for meteorology. This is on microsecond scales in 3 dimensions. And so you can actually do this to understand, it's actually not very well understood lightning phenomena, and this is another element that just serendipitously came out of the capacity of the telescope. Someone has seen these plots before. How do you measure the quality and the impact of a telescope or an instrument? An experiment growing into an observatory is really evident in these few things. I've run past them very quickly. We've seen a huge development over the last 3 years. We've got a very big and a very robust group, lots of collaboration, and a very expansive set of co-authors across 30 different countries. Now, I want to put this quickly up. These are from Dennis Crabtree's plots where he compares facilities across the world at all wavelengths over a variety of metrics. If you measure over 2017 to 2022 the median impact per paper, this is ground-based facilities, by the way, because Hubble would blow this off the scale, and so would JWST, so just putting that out there for the obvious. And what I can highlight various ones on here. What I've just highlighted here is the radio, radio interferometers. LOFAR's at the top here, SMA here, and altmetric scores. This is non-citation metric scores. And the one I want to show you is if you know where the bodies are buried and you know how much the operations cost, you can also look at things like this. And Sophia there at $1.1 million per paper wasn't getting us great value for money. But this is where, when you're an efficient observatory, you really start to show the value for money. And this is just the last one. Your impact value for cost, and LOFAR is in the top 3 in the world. So, how do you then, if you've got a good instrument, make sure it stays competitive? How do you, well, these are my opinions now. You have to keep your expertise in-house. You have to keep them interested. You have to know the field of play and what everyone else's plans are. And you don't be afraid to compete as well as collaborate. We're going up to LOFAR 2. I'm going to run over this fairly quickly. We are basically, do I check all of the things on the list? Yes. We're making sure our wavelength window is broader. Yes, we're doing greater dimensionality. And yes, are we being greedy? Absolutely. The main concern here is now we can do dual bands. We can do our low and high frequency at the same time, and we can do them with a better calibration and faster. This is underway. Compared to SKA low, which will be coming in as in construction right now, I told you already the magic we have is in the resolution capacity, but we also lower frequency. So SKA low only goes down to 50 megahertz, we're all the way down to 10. I'm going to skip over this. This is actually our first light with our test array for LOFAR 2. So we're very happy with this. We know it works. We're anticipating first light 2026. The hardware has been purchased and our construction will begin at the end of this year. So, in the 2028 landscape, knowing the field is vital. I'm not including everything here on this wavelength list. These are just the big guns. And the reason I say there's a radio renaissance on the way is because the scale of these projects is unprecedented at these frequencies. Square kilometre array, 1.8 billion pound projects, and increasing in cost as we speak. Incredibly ambitious. 3 sites, 2 telescopes, 1 observatory. You see the details here. Again, I'm not diving into this very often, but look at how many collaborators we have. This is the level of collaboration you need now to afford these, which is really important. Radio astronomy up until now has had a high barrier of access, and we're at our ALMA point, because these facilities will be delivering black box solutions, actual final products, not intermediate products. So that bespoke one-of-a-kind radio reduction field is gone. So when these come online, the radio community is inevitably going to expand to your ALMA black belt astronomer, but to your non-black belts. And so the investments are on scales we haven't seen before. So I'm going to leave with these last couple of slides just for you guys to think about. These flagship investments are only giving small percentage access to most of our radio astronomy communities because it costs so much. And so where do research communities stay competitive if they're smaller? So greed is good. We're looking at lower frequency upgrades. These include going lower again, we're now looking at 5 megahertz. We are now in feasibility studies to look at this, maybe catch the solar minimum. If this is feasible, we're going to do a new dipole design. We're going to leverage the existing infrastructure that we have. We could also go higher frequency. These infrastructures and the footprint we have in Europe is not to be gained again. So we might be going up, and if you just put about 100 dishes at each footprint of LOFAR, you could actually get to nearly the sensitivity of SKA mid. And that might be fun as well. So, apart from wanting to kill Elon Musk, which is on my to-do list, Starlink satellites are a major problem for us. Obviously, also interference is continuing to be a problem for us. We mitigate for now, keeps us viable, but this will be an issue in the future. And the very last one is, we can do this only if we can afford to take the data. It's the processing and the storage. The numbers, the data is just overwhelming, and it really does keep me up at night to know how we're going to afford all of this. So, I'm going to leave you with this. The low-frequency universe is about to become a huge new discovery space. If we can afford it, and if we can have the resources. For small communities, solving bottlenecks, finding a unique capability or a niche will be vital in that new field. Thank you.
Thank you, Jessica, for just amazing images. And so we have time for one question while we set up for the next talk.
Just a quick comment. I'm really excited about this. I think the renaissance is already here. One big concern I have is whether there's enough coordination with multi-wavelength data to interpret the radio data. The major weakness, of course, is you guys have no redshifts. And things are not radio loud anymore. It's just, little. So to really extract science out of it, I think it requires actually a lot of coordination and planning. And I hope that's being discussed, but that's really critical.
Yes, absolutely. And whether you follow up or you're a pathfinder, that's really the hard ask. So which Vera Rubin optical event is a radio source, worth following? These are questions which we need the theory for.
Thank you. Thank you, Jessica. So the next talk is by Satoki Matsushita, and he'll talk about Greenland Dempsey.
Okay, I'm Satoki Matsushita, one of the LOC here this time, and actually I'm the PI of the GOD project, and also EHD Taiwan representative, means that I'm one of the EHD board member, which Jeff doesn't like. Oh, thank you. Yesterday, well, I really did the PhD. Yesterday, Jeff Weissman showed the pretty nice NASA pictures. So this time I brought the pretty nice black hole pictures. It's a sticker, so I put that there. So if you like it, please take it. Okay, GOT, Greenland Telescope. Actually, this was initiated by Paul, to image black hole shadow. That's the primary goal of this project. Paul initiated, and then what he did is that as soon as Professor Makoto Inoue of the NAOJ VLBI group retired, Paul quickly grabbed him and come to Taiwan, and he agreed. And in 2009 April, Inoue-san came to the ASIAA with postdocs Keiichi Asada and Masa Nakamura, and that triggered the start of the ASIAA VLBI group. Then the key is that in 2009 December, Keiichi convinced Paul that we should bring the telescope to the Greenland, and then from there the Greenland telescope has formed. Well, the story by the Keiichi was the first talk of the Monday, so if you want to hear more, talk to Keiichi. Then why Greenland? Extend the baseline length to the whole Earth. That's the VLBI, the key to image black hole shadow. So that we decided to put the telescope in Greenland. And the construction part is that the team already talked, so that here, after construction, commissioning has started from December 1st, 2017. The telescope, we have 3 receivers, 86 gears, 230 and 345, installed at the primary focus, not the primary focus, secondary focus. And 2017, well, December 1st started. Already December 25, that the Christmas, that me and my postdoc at that time, Kevin, got the first astronomical first light. And then only 1 month later, we joined the EHD dress rehearsal at the 230 GHz and did the interferometry with ALMA and South Pole telescope. Then we got the fridge. So that within 2 months after telescope construction finished, we already got the fridge with the 230 GHz with ALMA, 9,000 kilometers far away. So I think we are really the fastest record to get the fridge after telescope constructed. And now we already did a lot of VLBI observation, and so far 90 observations we did, and the 2 failures, especially the first 2 years, that when we are not really experienced enough, but after that, even in the COVID era, make the telescope remote observation possible, and with the really close connection with the engineers at the Thule Air Base, we did all the observations. Then recently we published the first result from GLT. That this is the MA7 with the various frequency, maybe many people showed. And here, this is the past GMB at 86 GHz. And 2018, ALMA and GLT joined for the first time with the GMBA. That makes a huge difference because white is the original GMBA image, GMBA, that this is UV coverage, with the GLT and ALMA and ALMA GLT baseline. That creates a really good north-south baseline coverage. And we succeeded to image the ring structure with the jet structure for the first time. The EHD image only ring that because the telescope number, UV coverage is and the sensitivity is not good enough to detect both. For the 86 years with the GLT and ALMA, finally we see the black hole ring structure with the jet with the spine too. That the actual radius is bigger than the 230, so that we think we are looking at the actually accretion flow around the black hole. So, what do we want to do next? Of course, that Jeff talked, that all those EHD observations we are joining every single year, GMBA observation every single year, and also we formed East Asian VLBI network for anti-high frequency we are doing. And one of the things, but for the GLT future, that we want to observe toward higher resolution. The observation is like this, 2017 image. But actually, this structure is the mix of the photon ring, accretion flow, jet, many things combined. And especially key important point is that the photon ring that contains the information of the GR. That this original figure is this one, but for the light directly come from is including the whole astrophysics and GR together. But if the light bended by the black hole and come to the observer, then this GR effect was affected by the light. Light was affected by the GR and come to the our side. And more, then that it's getting sharper and sharper, and that contains more and more GR effect, especially near black hole strong gravity, so that separating this, that the light from the GR affected and take out is that the purely study the GR, really the physics, basic physics, and surrounding is the astronomical physics, that astrophysics, that the accretion flows, jet, that so much kind of things. And that separating is really the key. From the GR affected, so VLBI at 690 gigahertz. The GOT, the physics, Hawaii, phase SMA, JSMD, and phase ALMA. And with this, we can reach to the 4 microarc second resolution, which is roughly 5 times better because of the GOT join 230, the 230 and goes to the 690. And so that also here I have to mention that for the ASIAA, every single project is started, initiated by a program. And those 4, only ASIAA is related to. Only us can do this test. So that it's very important that really the Paul made a key for this project. But of course, 3 baseline is very difficult to image. So that the key is that they combine with the 345 gigahertz frequency synthesis is really, because 340 we think 345. 690, that frequency, the emission from the plasma near the black hole is very thin, so that we can combine the 2 frequencies each other. But the 230 is more affected by the inflow, outflows, these kind of things. So that the key is that 345 or 690, which is really closely look at the black hole. So actually, KG and Pei-Ying made a simulation that if only at 230, each image will be like this. But if we combine 345 690, we can separate the photon ring and something outside, which is really the key for this project. So actually, and so that we really tell the GR what pure physics we can talk about. Image will be like this. And of course, getting better resolution means that we can see more black hole shadows. And based on the current study, I think we think we can see 5 more black hole shadows. So that currently we're regulated by 2 sources, MA7 and Sagittarius star, and even 345 may be difficult. But if we go to 690. We can do the 5 more, which means that we can start start the research with a statistical study of the black hole shell, which is another important point for this study. So, to do that, GOT have to go to the summit of the Greenland. Currently, the telescope is located at Tule. Recently, the name changed to the Space Base, and but this is the sea level, so that we cannot reach the 690 gigahertz. But at the summit, there's a summit station there, and pretty flat. I went like a few years ago. And the opacity of the summit at the winter is that it's good enough to do the 690 gigahertz. So we want to move it. But 690 VLBI is pretty difficult. We know that. But we have some experience. We are the first one. As SMA, Smithsonian and the ASIAA, we are the first one in the world did that 690 gigahertz interferometry. And well, I didn't show my result, but many people did that, published several papers. But well, even that was very difficult, but we have experienced how difficult it is. We're not doing it from scratch. And we also studied that the phase fluctuation as a function of baseline length. It reached up to the 1 kilometer, increased with the 1 kilometer, but after 1 kilometer or longer, the phase fluctuation gets flat. So that the ALMA, it reached to the 16 kilometer, but even it reached to the 100 kilometers, 1,000 kilometer, phase fluctuation is almost the same. That's why we could do the VLBI. That's why we succeeded in EHT. So, 1 kilometer or longer, the phase fluctuation is actually, we know it is difficult, but we think it is possible. Challenging, but it's possible. The only problem so far is the budget. And of course, Paul said that by himself. How to find enough resources? Actually, we know need Godfather, but Paul, we think, please stay another 2 years together with us. Okay, thank you very much. The only said that by himself. How to find enough resources? Need Godfather. Paul, please stay another 2 years together with us. Greenland, just come back. Okay, thank you very much.
So those observations will be simultaneous.
Semi-spontaneous. Probably few days.
If you want to
as Jeff also mentioned, that the M87 is the bigger mass, which means that the time variation is smaller, much smaller than Sagittarius star. So about a week difference, not much difference. Semi-spontaneous. Probably few days. But anyway, GLC mentioned, so I mean, is the bigger mass, which means that the time variation is smaller, not smaller than Sagittarius star. So about a week difference, not much. Anyway, GLT can also, so that's I'm not thinking that.
Well, almost at the end, and I think we not what future information, but rather about how and what I've been following Paul's path decades later, and that's almost at the end, and I think we have some company on computer simulations. Years future about life, how I've been following about paths and calculators. So the point that I had already understanding when thinking on computer simulations hadn't been thought in the same way before. I think that's what the years has been a leader on life. Just thinking about.
Also, you're the first time
I ran into question already 20 years ago at a conference, but since this topic came up in pulsars and VLBI being thought in the same way before, in non-star, because the pulsars are 2 point sources, and it's like nothing to the point by looking at the VLBI 20 years ago at a conference. Then over the years, the Fed policy and I believe actually one this week in non-star were talking a lot about sources that pulsar propagation is a complicated phenomenon, and that pulsars may intrinsically be very small, but they appear not so small because the multi-Pascal is kind of solving of that area space now, and not all is actually fuzzy. But unlike a black hole, when it gets figured out by installations. It's a bit like a star.
Intrinsically very small, but they appear not so small without 20 Pascal. In fact, it's also that from the A star.
Because the black hole actually is quite size. Pulsars are emission of peacocks and smaller than the size of the black hole. So the intensity, because the still very white pulsars are seen when they are on kilojoules. These are very white sources. They are billions of times higher in the whole atmosphere at the emission point, and therefore propagate as a truly coherent light source. And then whenever when you image it, each of the spectral images that you see in the sky, interference pattern that we can actually image with VLBI. And I'm going to explain a bit about how this field has evolved over the years that I've looked at. So just to, in fact, the first data set that I became aware of that attempted to image pulsars with VLBI is by Wilson Company. And VLBI, and I'm going to explain a bit about how this. And just to demonstrate scintillation as a function of time in minutes. This is our receival, and frequency. This is a fairly small amount of frequency. There's more data, but then for you to see the scintillation, you can see it scintillates, goes in and out of constructive and destructive interference over a tiny fractional and that's one tiny fractional frequency change, so as a percentage time. 1,000 change in frequency results in a change of the interference pattern. In VLBI, this is a baseline between green band and placebo, and this is just the raw visibility, so the product of the voltage between the two. Here you see a crisscross pattern that people have studied between them over the years. In the VLBI, I'm actually not aware of anybody who's shown such a pattern. Because visually, physically, everybody has such a pattern. This is just the VLBI data. But what's kind of striking is that the positive visibility all the time, they have a down pattern. And the blue visibilities on the actual up pattern. That does not happen in any other source in the sky that gives scintillation results in asymmetry in visibility. And that's because objects blue and red correspond of course to the source being on different sides of the phasing center of the baseline. And this just tells you that the Doppler shifts of your visibility are asymmetric because the photon is moving. And now when you put a blue and piece it all together and image what's a scattering disk. We called it a disk in the past because they imagined it was identical in the past. When you actually phase it together, so we phase stabilize an image, we actually see that this is a locus of images that is almost perfectly straight. I'm showing some of these. To get there. And this is, this is 10 million. These are sub-million-second fluctuations from the straight line, that is that you can now ask what's what's happening in the medium that causes both an image made along a straight line, kind of a cloud image off to the side, and the path is called this. Combined more graduation is from this really a terrible word for what's going on in the kind of medium. One of our mediums collaborators passed away during both with the Geoffrey belongs to this subject. Now, if you combine those words, you can actually make highly precise measurements using VLBI and these scattering screens. Because you measure the angle and the time delay, you can measure distances to these screens to parts per thousand. So measure the distance to a part per thousand is at a distance of 100 parsecs, non-trivial step forward. So we can talk about pulsar timing arrays for interferometry waves. And given the distance to the pulsar, you can actually get a precise distance to a gravitational wave source by using that information. And all this up new tools that have really been thought about traditionally. Now you can use your screen as a new telescope, an AU-sized telescope, 100 AU-sized telescope, to image the pulsar. In these days, the voltages coming from different lines towards the interstellar medium, and now you have a billion-kilometer sized VLBI array, and you can now image the deflection, apparent deflection motion of the pulsar hotspot as it goes across the sky. So you can see a few kilometer change at the kiloparsec of a pulsar emission. So this is picoarc second astrometry that you can enable by using the interstellar medium as a coherent telescope. You know which line of sight, which line of sight any piece of radiation came from. This is just again a new way of using first VLBI to image your lens, and then this new cosmic lens by using the interstellar medium as a coherent telescope, because the pulsar is so small. Which light pulsar, it's just amazing that the visualization is unresolved at the scale of kilometers, and that you just have this little hotspot moving across the sky as over milliseconds. The pulsar is so small. So we've been thinking about using this coherence, and we combine this VLBI. We'll ask you questions about the universe. In particular, there's been a new class of objects discovered in recent years. We'll hear about this. There will be a colloquium next week by Duncan Lorimer, one of the co-discoverers of FRBs, who's passing to Taiwan on his way to Hong Kong to collect the Shortwise. And he's kind enough to stop by. There was a colloquium, a public lecture on Wednesday. On Wednesday or next Tuesday. Please do come and here will be a about the adventures of what FRB field started. FRB, more about it other than that. I think that was amazing. Not so much that they're energetic, they're not that energetic. Total energy, intense. They form an interference pattern to the propagation. So you're detecting not just the source, but you're detecting the interference of all lines of sight. This allows you to, for example, measure time delays. You have microlensing, something which started when I was a student. Normally, if you see a star, a star you may think is small, but the two images of a star and a microlensing are too far separated to form an interference pattern. They act incoherently. In the case of an FRB or a pulsar, they will interfere coherently, and you can measure the time delay between these images down to sub-nanoseconds. Normally, to a star, 1,000, when you get megawatt. But it's a totally different concept and regime of what you can measure. That there was no other tool that you can measure time delays to a nanosecond or to a distance of a pulsar. So you can now think about things. You can measure about measuring extra galactic planets. We talk about extra solar planets and everything. Now that you can start this inventory of planets and the galaxies. That's what it's only tool. Hard to see what you can measure otherwise. There's no other tool. So this is where I see the potential that these FRBs, which we're discovering. Different stories, a poster of it always as well. Galactic is over experts here. One of the new FRB initiatives in Taiwan. This is what it's only tool. Hard to see otherwise at such distances. So this is, there's another piece of history that I've learned over the years. Again, I started off some very different, but all may remember that there was something called extreme scattering events in the 80s and 87. There was a Nature paper that was mysterious at the time because there was a plasma magnification event of the background quasar that has estimated how much plasma you need to cause this unreasonable, it would be unattainable in an medium. And many times when I first looked at it, when Goldwatch said, oh, this is an interesting problem, because the leading explanation is either exploding dark matter or superconducting cosmic strings, everything else is physically forbidden. I thought, well, this is an interesting problem. It's a very obscure one. Not many people have really thought through. what these events were, and they kind of was unsolved for 30 years. And recently have managed to dig up some data. Students from Hungary and managed to find actually the data set that saw an extreme scattering event of DNA, pulsar, spectrally the pulsar image, that's quite data, and delivery becoming next week. Build a model where this can be explained by this geometric projection effect of two-dimensional structures into interstellar medium. I'll give examples of how coherent VLBI of coherent sources, being a completely different regime of the information you can extract, allow you to create completely new things, measure new things that we don't normally think about. Two-dimensional structures in the interstellar medium. Just the conclusions here that this opens a field of what I call wave coherent information limiting geometries, where every line of sight stays coherent and you're always measuring interference patterns. Normally, some people call these diffractive effects. I'm just going to call them interference effects. A lot of confusion in the literature of what the word diffraction alludes to. I mean, just the confusion that different people use that word for different phenomena. So anyway, I'm going to advertise it next week. We will have a meeting in here focused on all these issues. And I encourage anyone interested in talking about and hearing about the latest developments in this field. Diffraction. So anyway, I'm going to advertise it next week. We'll have a meeting in here focused on all these issues, and I encourage anyone interested in talking about hearing about the latest developments in this field. For the FRBs. The arrays that we have built, and that's nearing completion, and we're hoping to have this on the air in the next few months. We got about $1 million worth this array for the FRBs. But the array that we have built, and that's nearing completion, and we're hoping to have this on the air in the next few months. We got about $1 million worth from external funding, and perhaps a similar amount of institute funding. But again, it's dominated by non-recurrent costs. So that's for about 250 elements in a single station. Our current optimization is to expand this to by a factor of 10, and we're hoping that the cost hopefully only doubles if you have 10 more elements.
So they will be placed in different sites.
Yes, so the main station, if for any of you who have a chance to go below Taiwan, there's something called True Sun Botanical Garden. Beautiful poster out there with a picture of the array there. It's in the mountains, well shielded from interference. It's off limits to anyone except for the researchers. So it's not quite as exotic as Greenland, but much warmer. And you can go there in a 2-hour drive. So and there are people here, many people here in the room who've been there. And there's a very quiet zone that is well suited for this purpose. To localize, we have stations out on various distances. So Taiwan, of course, is an island. Get long baselines, you can go offshore to Green Island and to Dongsa Island, and to increase your localization.
What sort of FRB detection rate do you need before you start to have a reasonable chance of catching one of these micro-lensing events?
Well, first of all, since people are asking about the FRB practicalities, so this new array in Taiwan is unique that it monitors the whole sky all the time. So before, China, I'm wearing a China t-shirt, leads the number of FLBs discovered by a factor of 100 over the rest of the world combined, because it has a 100 times larger field of view than other telescopes. This is going to have another factor of 100 times larger field of view than CHIME, so it really sees the whole sky. There's also a sensitivity, of course, a flux limit, so this is not as sensitive, so the total rate will not be higher than CHIME in the first phase. The micro-lensing, so the typical number is dominated by stars, unless you think dark matter is compact, which I'm not going to assume here. Stars we know exist. How many stars exist? Every time I ask somebody, anybody who has their favorite answer, please let me know. The omega in star, I'm going to take a number order of magnitude 10 to the -3. If anybody wants to give me as a first digit on that, please do let me know, because I think people who I asked, it varies by factor of about 5 between different people. So do let me know what you think omega star should be. We need to know that question to answer that question. 4 10 to the -3 is about 1 in 1,000.
All right, thank you, William. So that concludes our all presentations, except the final part that Paul gave. But before that, I just want to have a few acknowledgements. I think I want to thank everyone for coming. This is part of visiting a memorable week that has, many of Paul's friends and colleagues gathered here to celebrate his scientific competition and leadership. So we had this conference wouldn't be possible without generous support from the Institute, Willie, and thank you. And also we have funding from the National Science and Technology Council. But also we had a generous contribution from Paul's former student. Fortunately, he's too busy making money, so he's not here, except joined us actually on Tuesday afternoon and evening at the resort. So I kind of have a mixed feeling, because ever since he made that contribution, I become Paul's less useful student. And he sponsored the dinner last night, except the sticky tofu. That was sponsored by Paul. But of course, the conference, we have many organizers, and I'd like to just invite the scientific organizing committee, if you could come up to the stage. So I think Ina Palau did not join us in person. I believe everybody else here. So if you think there are too many talks, they're the ones who blame. Of course, the people actually did the real work are actually in the LOC. That, they arrange many things from bus rides to hotels, a lot of activities, and also manning all the technical support and taking photographs. So I'd like to invite them to join us here. Please. Conference to also coincide with Paul's retirement, and we're so concerned that we'll slack off. So that's why part of the reason you actually get in 2 talks. But also we prepared this book that lists all the to-do lists for you. That I will present to you, Paul. Why don't you come up?
So I should leave now. See you later.
All right. Maybe you can open this to see what this.
Is it food?
It's edible.
Don't break it.
Getting more and more complicated. It's like Christmas time.
Yes, Christmas time for
Ah.
So it's an album of photos, and also it has signatures of all the participants.
Holy smokes. Oh no, that was project. Well, thank you very much. This is great. Thank you.
All right. So all go to your seat, and then you have the floor.
I don't have that much to say, really. You know, the first 2 days of the meeting was at the resort, where quite a number of you were there. I was forced to relive my life. You know, the thing that happens a minute before you die, when everything that's important in life flashes in front of your eyes, and people said nice things, and people said not so nice things. I remember them all, especially from the youngest student. Bravo. But it was actually a lot of fun for me, right, to recall not only myself, what happened, but it's the shared memories, right, that's important. It's not just I remember, but all of you who experienced with me, I'm glad that you also remember, because they're very important to me. All the things that have happened over all this time. My career can clearly be divided into 2 parts. The first part was in the US, that's dominated by my students and postdocs. And then the second half, which was in Taiwan, dominated by my staff here, right? And also the naughty student who was the last one. But anyway, we did a lot together, which is great. But that was the first 2 days, right? The next 3 days is all about looking forward and all the wonderful things that people are working on. It's mind-boggling. It's also extremely satisfying, right? If you were a parent, what your fondest wish is that your children will exceed you. They will do more exciting things. They will accomplish more. They will become better, right? Which is what I've always believed in, that the future is always better and the better things are coming, right? So you are a demonstration of that throughout my career of what I've always hoped to become true, right? So there are different styles of doing science, as you know. Here's the Reinhardt-Genzel school, you know. Crush everyone around you and achieve that singular scientific objective. And there's my style, which is that, you know, I am here to promote the possibility of many other things to happen, and this is what I'm proud of, right? That all of you have achieved so much and made contributions in so many different directions. It's truly amazing to me. So I thank all of you for coming and sharing your work and sharing the last 40 years and 50 years of my career. I'm very proud of all my students and postdocs, and they are truly representative of what I've always hoped for. And this is what I mean when I say my students are better than my children. You know? My children are unfinished work, but my students are finished work. Which I think if you are a teacher, as you will have your own students, this is what you should hope for. And when your time comes to your retirement party, you wish you could have this as good as this. Okay? So that's all. And let's continue. What's the next thing to say? Let's eat!
Thank you all for coming.
Go back to work.
Now I see what happened when you guys shoo me away. You're getting me to sign, weren't you? That's right.